Thank you. So before I joined Hightable as a data scientist, I was actually an astrophysicist. So I thought today, during this brief slot, I'd share some of my observations about differences that I've noticed between the way I approach data as an astrophysicist and the way I approach data as a data scientist. So first big difference is that in astrophysics, uncertainty is everything. I think about data as an astrophysicist in terms of how much it helps us reduce our vast ignorance about the universe. So, and how much we can constrain the parameters of our models of the universe. Whereas in machine learning, decisions are everything. So what I care about is making predictions and making good decisions based on those predictions. Here's an example from my astrophysics work. This is a spectrum of a quasar. It's a bright object powered by a supermassive black hole. And it's plotted for other astrophysicists. And you can see I've spent as much ink on the error, the uncertainty on the measurements in the bottom panel as I have on the actual measurement in the top panel. Now, when I want to explore the uncertainty of the parameters in that model, again, what I emphasize is the bounds on our knowledge about these parameters. So this gray ellipse is the boundary of the plausible region of parameter space from a fit to that data I just showed you. So the reason we care so much about the uncertainty is because that's really what tells us, it's really what tells us the boundary of our knowledge about everything. So we might want to know not just about our knowledge about an individual quasar, but about the whole population of quasars. So I built a hierarchical model where we have parameters describing the population of all quasars in the universe, and those are inferred at the same time as we're inferring the properties of each individual object in our data set. So remember the fit in the top right corner, the gray ellipse is from a fit to an individual quasar. In this new plot, each of those gray ellipses is a fit to a separate individual object. And then we take those uncertainties into account when we infer the properties of all quasars in the universe. So I've given you an example from my astrophysics work of the emphasis on uncertainty. Now let me give you an example from my machine learning work at Hightable where the emphasis is on decision making. And this is using support vector machines to find boundaries in feature space. At Hightable, we face data problems like needing to tag incoming content or needing to classify new users. And one thing we definitely found is that when you just give users a free text field and ask them to tag content, the tags aren't consistent. You get a situation where most of the tags are only used once or twice in your whole data set. So the tags are just not consistent enough to be useful for grouping similar content. One potential solution is to just move to fully automated tagging. But we really found that that wasn't accurate enough for our purposes, and we wanted to have a chance for humans to validate those tags. We could offer users predefined categories, but when you have enough categories to be useful, people find that to be arduous to sort through those lists. And if you don't have enough categories, they find it to be somewhat limiting. So the solution we ended up implementing was to train classifiers on the best tags from our existing data and then suggest a limited number of tags to users for validation. And that forces us to make a decision. We either show a tag or we don't. And we don't get to just assign a probability to a tag and consider ourselves done. Of course, that's an oversimplification, this distinction. So here's a counterexample to that distinction. In astronomy, we often are forced to make hard decisions, like which objects we're going to observe with a telescope. There are a limited number of world-class telescopes, and we have to make decisions about, for instance, Hubble is oversubscribed by 600%, so we have to make decisions about what we're going to point Hubble at. Another way you see this distinction that I do think actually is meaningful is that in machine learning, the tools we use to evaluate results are often things like F-scores and lift and area under ROC curves that emphasize the quality of our predictions. Whereas in astrophysics, the tools we tend to use are things more like error bars and p-values and posterior distributions that emphasize the uncertainty on the parameters of our models rather than on the predictions of those models. The predictions serve to validate the models, but aren't our main point of interest. Another way, a sort of similar distinction that I've noticed is where we spend our computational effort, although this can break down too. In astrophysics, traditionally, in astronomy, it was very hard to acquire our data. Historically, it's been hard to acquire our data. Think of Tycho spending 30 years acquiring those 2 million data points. So we tend to spend our effort computing the very complicated physical models we're computing rather than on the actual handling the size of our data. Whereas in machine learning, we're often obviously dealing with large data sizes, and that's where our computational bottlenecks occur. So to give a counterexample to that distinction, as Deborah mentioned, that situation is changing as our tools advance in astrophysics. To give one example, there's a radio telescope under construction that's going to generate over 1 terabyte of data every second after considerable pre-processing. So let me just wrap up finally by saying that I've painted a picture of these differences, but obviously, as several speakers have mentioned, the tools from both fields really are useful in each field. So I think we have a lot to share with each other. Thank you.